Ever wonder how doctors map the brain's tiniest blood vessels? It's not just about seeing them. It's about accurately tracing capillaries thinner than a human hair, which is critical for stroke diagnosis, surgery planning, and brain-computer interfaces. But here's the problem. When experts manually draw these vessels, they often disagree. And that's exactly what this study investigates. Digital subtraction angiography, DSA, gives doctors a live view of blood flow, but segmenting every vessel, especially those microscopic capillaries, is a nightmare. Current AI tools struggle with these tiny structures, which are key for spotting tumors, tracking stroke recovery, and placing stents safely. Manual segmentation by human experts is still the gold standard, but it's time-consuming and, well, human. Two experts might draw the same vessel slightly differently. That's where this research steps in. They wanted to understand how much these differences matter and how to account for them. Here's the cool part. They gathered 66 DSA images from 11 patients and had 2 expert annotators trace the vessels. Then they created 2,000 image patches, tiny snapshots, and asked 11 other doctors and scientists to label them. The result? Some regions had complete agreement, but others. Total chaos. When both experts agreed a vessel was there, 90% of raters agreed too. But when one said vessel and the other said no, only 16% of raters agreed with the first. That's a huge discrepancy. It shows just how subjective this process can be. To measure this, they used a tool called clDice. Think of it as a scoring system for how well 2 vessel maps match. But here's the twist. Traditional methods favor larger vessels. So they tweak the formula to be fairer to tiny ones. Imagine adjusting a game's rules to make it more equitable for all players. The takeaway. Manual annotations aren't perfect, they're pseudo-ground truth. But by understanding where experts disagree, we can train AI models to be more reliable. And the best part? The researchers are sharing all their data and tools open source. Imagine the breakthroughs that could come from that. So next time you hear about AI in medicine, remember, it's not just about algorithms. It's about understanding the human side of data. Thanks for watching. Hit subscribe for more deep dives into science that shapes our future. Let's dive deeper. The team used a metric called clDice to measure how similar 2 sets of annotations are. Think of it like a scorecard that tells you how closely 2 drawings match, not just whether they overlap, but how close they are. In their experiments, they compared annotations from 2 experts, A1 and A2, across 66 brain DSA images. The results? Their scores were pretty high, around 0.83 to 0.84, but there was still variation. That's normal, right? But here's the twist. When they compared these annotations to 7 other experts, the scores dropped, sometimes significantly. For example, one annotator, A1, scored just 0.618 on a patch compared to A2's 0.759. That's a big gap. Now the researchers didn't stop there. They tweaked the clDice formula to account for distance, not just whether lines overlapped, but how far apart they were. They found that when they adjusted for a 2.5 pixel threshold, like a tiny margin of error, the scores became even more consistent. This modified clDice gave them a clearer picture of how reliable annotations are, especially when dealing with complex structures like blood vessels. What does this mean for the field? The study highlights a critical issue. Even trained experts can disagree, and that uncertainty can mess up AI training. But the team didn't just point out the problem. They created a new dataset with over 2,000 labeled patches, plus open-source tools to refine annotations. This isn't just a paper. It's a blueprint for building more robust AI systems. So the next time you see a medical AI breakthrough, remember, it's built on the messy human work of getting those tiny lines right. Thanks for watching. Hit subscribe for more deep dives into the science shaping our future. Until next time.